Good morning. Yeah, you'll be the finger.
Okay, I'll be the finger.
Yeah, we decided to go for a double act because there's some stuff in our talk that I don't understand, and there's some stuff in our talk that Luca doesn't understand, so we better do it together. Probably, if you look at the title, most of it is bread and butter to you, but I want to pick up two words, two keywords if you want. The great enrichment, which is we fiddle with the elastic stress-strain relations to add some extra terms there. And also, the last one, concrete. I think there's a few civil engineers amongst us today, I'm one of them. But I think most of you are either mechanical engineers probably, or physicists, or even better. Why concrete? Concrete is generally seen to be a bit of a messy material, difficult to control. But it has one nice aspect that suits us today, is that you can actually separate microstructural geometry from strength. Strength in concrete is governed by the water-cement ratio, and you can in a way control it independently from the sieve curve aggregates that you chuck in. Yeah, so that gives you something nice to play with. This is what we're going to do, so I suppose that's more what you would expect from us. Much slip stresses, high cycle fatigue, much is known on different sharpness and so on.
Good. Okay, when we talk about fatigue of concrete, of course, as metals, there are a lot of aspects affecting the fatigue behavior of concrete. Geometry, shrinkage stresses, aging, and blah blah blah. But as for metals, the most important aspect is the presence of non-zero mean stresses. Plus there is another problem, concretes work under cyclic compression as well. So we need a good tool, first of all, to take into account the mean stress effect. So by analyzing a large number of experimental data, we have observed that we can simply use the extreme stress in the cycle to perform the fatigue assessment of concretes. And in particular, when the load ratio is lower than 1, that is when sigma max is larger than 0. Sigma max, the maximum stress in the cycle, can be used as the design stress to estimate fatigue lifetime. But when your concrete works under cyclic compression, basically you get the mirror stress. So the absolute value of the minimum stress in the cycle can be used as a design parameter. So if you start considering the high cycle fatigue behavior of concrete and you plot the amplitude of the endurance limit normalized by using the corresponding reference strength, that is tension or bending under tension and bending, or the static strength under compression, what you see here is that there is a clear mean stress effect. This is true under either tension or bending. But this is also true, slightly evident, under compression. But if you use the design stresses as we defined them before, you can see that even if there is a certain level of scattering, the normalized endurance limit in terms of extremes of the cycle allows the data to fall within a quite narrow scatter band. So the idea is that we can directly take into account the mean stress effect by using these tricks, that is the extremes of the cycle, to perform the design. And according to this general idea, we had to manipulate the theories we are using in order to be able to take into account the mean stress effect. So, the first theory we need is the theory of critical distances. Of course, I'm sure that you all know this theory. Basically, the idea is that a component is in the endurance limit condition when an effective stress, which depends on a given material length, equals the plane material endurance limit. So now, since we'll be dealing with bending, everything is expressed in terms of maximum stress in the loading cycle. But the question is, how do we calculate the effective stress? There are different strategies. We can move a bit away from the notch crack tip. This is the point method, and the effective stress is at the given distance from the notch tip. Or we can average the stress over a line. This is known as the line method. Or finally, we can average the stress over a semicircular area which is centered at the tip of the notch. The common feature of these three formalizations of the same idea is that L is a material property which can be calculated by using a linear elastic fracture mechanics property, the threshold value of the stress intensity factor, and a continuum mechanics property, which is the plane material fatigue limit. But when it comes to concretes, the problem is that it's very difficult to determine the threshold value of the stress intensity factor, simply because they are super brittle. So we need then a trick to be able to estimate L, even if we cannot determine the threshold value of the stress intensity factor. And to do so, we can use simply the point method argument, and if we plot the stress, if we test a notch with a given rotor radius, we can plot the linear elastic stress field in the endurance limit condition, and we can find the point at which the local stress equals the plane material, so the unnotched material, endurance limit, and that distance is equal to L divided by 2. So this simple experimental approach is based on the point method. So this is the trick we'll be using to estimate L for the concrete we tested.
Okay, so we had one L now, big L, that's for the TCD. I'm going to talk about another continuum mechanics concept called gradient elasticity, where we have relation between stress and strain, sigma and epsilon. As usual, linked with the constitutive tensor C. But we also chuck in an extra term, which is the second gradient of the strain, pre-multiplied with a parameter then the necessity has to be length squared, so that's not a length scale, and we call that small l, so that's the gradient elastic length scale. Now there is of course continuum theory, I'm an American guy, so I like to find elements and implementations. It's not super difficult to implement it. Let's jump straight to how you do it actually. The beauty of this particular mathematical structure is that you can actually implement it in two stages. And the first stage that is your standard linear elastic stress strain relation that exists in any finite element code under the sun. So stiffness matrix times displacement equals forces. Yeah? As simple as that. But then those displacements are used in the second step as a source term on the right hand side there, pre-multiplied with some shape function stuff, don't worry about it now. And we've got here a system matrix which is it's almost like a mass matrix, not exactly, almost like a mass matrix and almost like a diffusivity matrix. Again, that should be available in most finite element packages. That together pre-multiplies the stress which is then your unknown. So these are now the gradient enriched stresses, because the L parameter, small l, appears inside the matrix. So that gives you a gradient enriched stress vector. The nice thing about those gradient enriched stresses is they are not singular at crack tips, at sharp crack tips. They are smooth. And that's was of course the main reason why that theory was put into existence.
Good. So we have two theories now, and the next step for us was, of course, running our experiments, because for me, when we started, it was very surprising to discover that no one so far has tested plain concrete under fatigue loading by exploring the effect of the notch sharpness. So we started designing our experiments. So we choose a conventional concrete mix, so this is a very basic concrete. And when manufacturing the samples, as Hannah was saying at the very beginning, what we did was playing with the water to cement ratio, moving from a value of this ratio equal to 0.5 down to a value equal to 0.4. So in the first case, the corresponding bending strength is 4.9 megapascal, and in the second case it is 6.5 megapascal. So as you can see, by keeping the main ingredients the same, by simply changing the amount of water we are using, we can really change the strength of the material we are using. But for the two batches, the microstructural features are the same, because the main ingredients are the same. And by spending a very long time, we came out with this nice number, 4 millimeters, which is the average inter-aggregate distance. That is the average distance between two adjacent stones. Okay? So, basically, it's the same material. So after that, we cast our samples. These are the plain samples. We changed the notch root radius. That radius was very small, and in the concrete wall, that one is a crack for them, and we simply use a saw to cut a slit. The other notches were cast in, and this is the shaking table we developed in Sheffield in order to test these samples, because the idea was investigating the endurance limit, so we needed to be able to run tests for a very long time. A very simple basic configuration, 4-point bending, being able to measure the applied forces cycle by cycle and the displacement. And basically what we did was using Dixon's method, the up-down method, in order to determine the endurance limit at 2 million cycles to failure. So this is the standard approach for the fatigue people. It's also suggested by different standard codes, so we didn't invent anything. We applied the theories we all know, or the approaches we all know, to determine the endurance limit for this material. Of course, when you get failures running your test, you can explore the material, the crack, basically the crack surfaces. And it's a very interesting approach or problem in the sense, because cracks were seen to initiate in these regions, so the highly stressed regions, basically. And the initial crack was due to the bonding between the matrix and the aggregates. And after that, the cracks were seen to keep propagating in the matrix. And actually, a small crack was enough to result in a faster fracture of the sample. We tested our sample at the frequency of 10 Hz, gathering all the pieces of information we needed at 1 kHz, and we were capable of completing a cycle after detecting the presence of the crack. So it was like crack there, bang, specimen broken. So that was very nice, because there was no plasticity, and our theories are all based on a linear elastic constitutive law. Okay, now we're going through the results 3 times now. First of all, pure TCD, pure theoretical distances. So we've got 2 batches, batch A, the weaker one on the left, batch B, the stronger one on the right. There's the fat dash line is the unnotched specimen endurance limit, and then the 3 other colored lines are the ones with the notches. And we fitted our L, our big L parameter, based on the sharpest notch. So we get an 2.9 on the left, and a bit of a surprise, but a nice surprise. We found exactly the same value on the right. Yeah, and that reinforces the hypothesis that we're dealing with a microstructural geometry parameter. Yeah, because remember, we have the same sieve curve of aggregates chucked into the concrete. 2.9. On the bottom you'll see a table with the errors. Because of course, I paint a very rosy picture, but there's no scatter, of course. We see up to 20% in the line method, but the area method and point method are typically between 5 and 10% error. So that's pretty good for such a crude first analysis. Okay, now we're going to keep some of those LEFM ingredients and now add a little bit of gradient elasticity in there. So, because we have finite crack tip stresses, we thought, okay, actually let's use those finite crack tip stresses. I'm going to check that against the unnotched specimen reference strength. We derived in earlier life a relation between small l and big L, which you see over there. And so we've just fitted big L from the previous experiments, you can now compute small l. And what we see again is, well, L is just over 2. These curves, so again, this unnotched specimen is the fat dash line.
Most of the estimates are on the safe side. However, the honest specimen is slightly below. Now, overall, the picture's not so bad. It's reasonably reassuring. But we thought, okay, can we do a little bit better than that? And why actually? Why is the drag one below? Well, if you go back to bending theory, let's go back to the tensile test first. We have, of course, a constant stress across the specimen, as you would expect, and there is no gradient in there in stress. Therefore, the gradient, remember the L squared term, lambda squared, that doesn't become active. However, if you bend it, you've got a linear profile in your classical theory, and that introduces the gradient effect, especially in the boundary, and the actual gradient enriched stresses are the red line here. So there's a slight deviation from classical theory. And we thought actually we should probably use a red line as a reference in the other graphs. So that's what we're doing with strategy 2. We need it there, Chairman, thank you. We also thought, okay, whilst we're deviating from TCD, let's just forget about the relationship between small L and big L. Let's just refit small L from experiments. And we had a little idea earlier that L should be equal to the average aggregate interaggregate distance. So we're taking now the maximum stress tip based on the gradient enriched on the specimen strength, and that came out very, very beautifully, where everything is within 20% and on the safe side. So we're very pleased with that.
And just since we are a bit late, the main conclusion is that we cannot do that with metals, because if we pick a sample and, for instance, we do something to the sample to increase the grain size, what happens is that the strength changes as well. But with concrete, you can keep the microstructural features the same by changing the strength. So, for the first time, eventually, we were capable of proving that the length parameters which are used in the critical distance-based approaches of all kind, if you like, because there are other formulations of the same idea, are based on the material microstructural features. And on the other hand, you need the strength of your material. So eventually we could uncouple the two aspects. L depends on the material, and the reference strength is the strength of the plane material. Thank you very much.